Esteemed PhD candidates, the doctoral board of this university, represented by us, has read your PhD thesis and the propositions that go with it, and we are ready to hear you defend it. Please take your seat. I call on Professor Mostovoy from this university to start the opposition, please.
Esteemed candidate, let me first congratulate you completing your completion of your thesis. I am very impressed by the number of different topics you discuss there and by the quality of research here. So it's really a great job you did. I have a few questions concerning two chapters, but maybe first a very general question. So when you calculate Rashba-Delstein effect and in chiral tellurium, yeah, you say that this effect is very big, yeah? And then you also calculate it in a few non-centrosymmetric material like nickel 1/3 niobium sulfide, and you say it's also considerable. And then I tried to compare them, yeah, so, and I looked at the figures, and in the case of tellurium, you said it's 10 to minus 8 Bohr magneton per tellurium if you apply current 100 ampere per centimeter square. And then if I look at this other compound, yeah, you measure it in, I forgot, 10 to minus 11 H bar divided by volt per centimeter, yeah? So how can I compare them? Can you help me? And which one is actually larger, yes?
Highly learned opponent. Thank you for reading my thesis and for your encouraging words. And thank you for the question as well. It is true that I used a different framework to calculate a Rashba-Delstein effect. The main reason was it depends on to which reference we want to compare with, plus by what kind of sources we were motivated with. So in that sense, I have used a different framework depending upon, for different chapters, in fact, yeah. Mm-hmm. For tellurium, for the most time, I use Boltzmann transport. And if I do the symmetry analysis, I express Rashba-Delstein effect in terms of Edelstein susceptibility. So for that, I have a unit in terms of H bar and so on. Mm-hmm. But if I want to compare with the experimental measurements, that's when I express my induced magnetization in terms of Bohr magneton per cell. Yeah. Otherwise, if I'm using Kubo's formula, then I have a slightly different unit again compared to the units in the Boltzmann transport. But the Kubo's units are different mainly because we wanted to compare with the other calculation that other people did.
That's all understandable, but yeah. Say if you like apply the same field, yeah, to tellurium and to this sulfides, yeah, which one would show larger magnetization, and can you say how much larger?
Thank you. I was coming to that anyways. Yeah. When I did the conversion, I found that tellurium, in fact, has the highest magnet.
Is it by order of magnitude or like several times larger?
It wasn't order of magnitude. Mm-hmm. It's in the same order. It's just some number, yeah.
Okay, then talking about Kubo formula. So in the very introduction, so that's page 10. So you have two contributions to Rashba-Edelstein effect. So these are equation 124 and 125, yeah? And the second one that you call even, you explain that that actually can be understood in terms of the Boltzmann equation. Yeah, basically, this is like a usual explanation of Rashba-Edelstein effect. Yeah, so you have non-equilibrium accumulation in the Fermi surfaces where spin is locked to momentum. Yeah, and then you get induced magnetization. And then you have also this odd susceptibility, which is the first term, 124. And what I would like to ask, what is the physical meaning of that term?
Highly learned opponent. Thank you for the question again. With regard to the equation 1.24, what I call it as the Edelstein susceptibility, but I call it as, when it comes to Edelstein effect, I call it as D odd, in the sense that this linear response is odd under time reversible symmetry. So having said that, this term exists only in the magnetic material. Mm-hmm. So if I have to calculate this for non-magnetic material, it would be zero. Yeah? And of course, other than the fact that it has to be magnetic material, it has to break the inversion symmetry as well. That's what I meant by T.
No, that's perfectly fine. So suppose you do it for this transition metal niobium sulfide, yeah? So where there is a magnetic ordering, yeah? The question is, what kind of physical, what is the physical origin of that effect, which, if you have an antiferromagnetic ordering, is non-zero, yeah? So.
Highly learned opponent, thank you for the question. Okay, for this one, if I compare, if I talk in the context of nickel tantalum sulfide that I calculated in chapter 7, so for this case, there's an antiferromagnetic ordering of magnetic moment for different sublattice. However, if I look at the momentum space, it has a band splitted, even without spin orbit coupling. Mm-hmm. And for me, at least, that satisfies the definition of altermagnetism in the sense that, okay, in the real space crystal, we cannot go from one magnetic sublattice to other magnetic sublattice via P3 symmetry. In that sense, and the magnetic ordering is collinear. So in that sense, it fulfills the criteria of altermagnetism. So as a result, that altermagnetism is the source of this equation 1.24.
Talking about magnetism, so in this term, actually, I don't see any, how to say, there is nothing that suggests that it only is applicable to conducting magnets, yeah? So you have some sum over energies. The question is, suppose you would have a material with a gap. Can you use this term also to calculate linear magnetoelectric effect? So you apply magnetic field, you induce electric polarization, you apply electric field, you induce magnetization. Can you do it using this term? So the one that is associated with Boltzmann equation obviously does not work in insulators, yeah? Yeah. But here I don't see why it shouldn't, yeah? So.
Thank you for the question again. In my computational work, what I did was I didn't think in terms of whether it's a metal or a semiconductor. Mm-hmm. What I did was I calculate the susceptibility by changing my Fermi level up and down, and I think that's equivalent to applying some kind of doping if you have a semiconductor or insulator. So, yeah, I think equation 1.24, you can have it even in semiconductor.
So it doesn't really matter for you whether it's insulator metal, yeah? Whether it has gap or not.
At least from my computational point of view, I was just shifting my Fermi level up and down, and that's how I computed.
May I ask one more question, Mynheer Director?
Very brief question, very brief answer, please.
Let's see. Well, this last chapter on this metal sulfides, yeah. So you concluded that if you take a non-centrosymmetric material and you calculate Rashba effect, yeah, and then you go to low temperatures and the spins order, yeah. In fact, that results in the reduction of the effect, yeah?
What's that?
So the Rashba susceptibility, it reduces because of the magnetic ordering.
Yep.
Can you explain why is that?
Briefly explain.
I believe that, thank you for the question, I believe that it's the interference between the band splitting that's caused by the spin-orbit coupling, because it doesn't have the crystal inversion symmetry, but there's also band splitting due to the altermagnetism. Yeah? So these two splitting, they interfere constructively or destructively. And in this case, I think it clearly shows that they interfere destructively.
So what you say is that if you take altermagnets, yeah, which say in center symmetric crystal, yeah, it actually does not give rise to Rashba effect, yeah, and that's what you get if you have a non-stereosymmetric material magnetic ordering, yeah, so antiferromagnetic ordering. Yeah.
I have to think on that, actually.
Okay, let's, yeah, so thank you.
Yeah.
Thank you.
Thank you. The opposition will be continued by Professor Buongiorno Nardelli from the University of North Texas.
Esteemed candidate, again, let me congratulate you on the completion of this thesis that I've been kind of following on and off, and I've been always very impressed by the work. So I want to start with a more general and maybe audience-friendly question. So if I had to ask you, what is the most important contribution that you are making to science with this thesis, what would it be and why?
Highly learned opponent, thank you for reading my thesis, and thank you for taking your time to come all the way to here for my defense. And thank you for the question as well. It's a very important question, I believe. So the most important contribution from my point of view is that, so we know that spintronic is an emerging field that aims to replace conventional electronic devices, which is based on charge current, or basically which we take full advantage of the electrons' charge degree of freedom to make a device, right? But spintronics, we are also making use of spin degree of freedom, and our goal is to make a spintronic device. So in that sense, I studied a variety of material that could use in such a spintronic device. For instance, what kind of structure we would need to generate spin current efficiently, that is, which can be used for carrying the information. And I also studied Rashba effect, which we can generate some spin accumulations or electrically. So I studied a crystal, specifically chiral crystal, and I found out that chiral crystal are a very promising candidate to be used for the spintronic devices. The secondly, I also did lots of computational work, and I think I laid some kind of, I wouldn't say a foundational, but I really propose different kinds of computational tools that you can use to study materials for spintronics devices. So it's not just the material itself, but the computational tools, the different kinds of computational tools that we can use.
So I think one of the themes of your work is this interplay between the symmetry, the spin texture, the band structure. So can you give us kind of a qualitative sense on how these things play together in determining the property of the materials that you have studied?
Highly learned opponent, thank you for the very interesting question again. All the material, I think it's all the material that I have studied during my research, they belong to non-centrosymmetric class of material in the sense that they don't have inversion center. Because of the lack of inversion center, it's a very, because of low symmetry, there's a very interesting interplay between the symmetry and the functionalities that you get out of the material. So when you don't have the inversion symmetry, because of the spin-orbit coupling, there's always a band splitting of spin up and down, which is different from the class with the inversion symmetry. Because there's band splitting in the momentum space, you can, for instance, induce net magnetic moment electrically, even in non-magnetic material, which is an Edelstein effect, right? But how does the induced magnetization look like? That is determined the symmetry, and the information of symmetry for the crystal system is actually encoded in the band structure if you plot the spin resolved band structure. And you can also plot it like a spin texture, which is the spin in the momentum space. And the symmetry analysis and the spin texture, they goes together, and that together dictates what kind of induced magnetization you'll have when you apply the charge current to the crystal.
You mentioned the importance of the band structure, and here you are using density functional theory. That is a technique that that is known to have shortcomings in the descriptive electronic structure of material. So how do you deal with the potential shortcomings of density functional theory in your work?
Highly landed opponent, thank you for the question again. I'm aware that the density functional theory method is not the perfect method to study many body problem, but out of many tools, computational tools, it's I think one of the best tool I would think to study the computational aspect, right? The shortcoming, one thing that I'm aware of is that since I'm using zero potential based density functional theory most of the time, it tends, if I'm studying semiconductor, it tends to not give me the correct band gaps and so on. But I could improve the band gap by using different zero potentials. That's one way to do it. But having said that, okay, that is only for improving the band gap, right? But like you said, there's still a problem when it comes to band structure, like not just the structure itself. Forget about the band gap, yeah. Well, people tend to improve it by using a more complicated, advanced DFT method. But for my study, I haven't used it, so I cannot really comment in detail how I would use it. But in future, I would be interested in going much deeper, more advanced DFT. Yeah.
You also mentioned in the first answer that you contributed to computational developments, and I was wondering if you can expand on that a little bit.
Thank you for the question, highly learned opponent. So I used a different DFT package, but for the post-processing of my plane wave functions that I get from the DFT, I use primarily power flow, which is the projection of plane wave onto the localized pseudo-atomic orbitals. So one thing, at least for me, is that using this power flow, I implemented a Cuvier formalism to calculate different linear response tensors. For instance, not just spinel effect, but Edelstein effect, charge conductivity, and so on.
How much time do I have? 2 minutes. Okay, in these 2 minutes, where do you see the field going?
Thank you for the very interesting question again. Since my work is mostly computational, and I did lots of DFT, but I see that the field, as I can see, is inclining more towards the machine learning, neural networks, and stuff like this, which I have not done during my PhD. But these heavy calculations that I did during my 4 years of PhD, in a couple of years from now, I believe, I speculate at least, that it can be done by machine learning method, which could be very interesting. But at the same time, I feel like there's a lot of work to be done before we actually drive straight into the machine learning, because machine learning by itself is nothing. We have to train the machine right, and for that we need a good data set to train the machine. And for now, it's the challenge is to actually generate accurate data set for machine to be trained.
Thank you.
Thank you, Professor Nardelli. The opposition will be continued by Dr. Lokonte from the University of Groningen.
Thank you, Mr. Chairman. Esteemed PhD candidate, first of all, I would like to congratulate you for this very nice piece of work. I really enjoyed reading it, and even if I'm not a computational scientist, I like the fact that sometimes you also try to give an intuition of like a more descriptive argumentation of your work, so to make it accessible also to non-expert in the technicalities of your calculations. And so also for the benefit of the audience, I would like to start with discussing very quickly the choice that you had for the cover of your thesis. So you can explain us, why did you choose this figure for the cover of your thesis? What's the reason for that?
Very learned opponent. Thank you for reading my thesis, and thank you for the question as well. When it comes to the coverage of this thesis, actually I have to mention, I want to acknowledge that one of my master's students designed this cover page, Bradley. But I made the choice, the snail. Some people associate the snail with the slowness, but that's not how I think about it. But this snail has a helical pattern, which is a kind of a structure that I have in the chiral crystals that I studied. Not all the chiral crystals, but most of them have this some kind of helical structure in it. And chiral crystals, depending upon whether they have a left-handed chirality or right-handed chirality, they can give us very different properties. So similarly, I read in literature that the snails also comes in left-handed helix and right-handed helix. And depending upon their handedness, in this sense, they can have a different kind of biology for themselves as well.
Indeed, that's right. And that's why I wanted to then proceed with the second question, that is, what is the consequence of the fact that in your material you can have two different chiralities? What is the result of that?
Very learned opponent, thank you for the question. The consequence of a structure having a chirality sense is that there are certain properties that are very sensitive to the chirality, the handedness of the structure. For instance, here I studied the Rush-Federation effect a lot. In this case, the Rush-Federation effect, the net magnetization that you generate electrically is sensitive to the chirality of the crystals. For instance, I could get a positive net magnetization for right-handed, but but if I have a left-handed chiral structure, I would get a negative sign. Yeah? So this is just one of the examples.
Okay, thank you. So now I would like to discuss figure 1.7. It's one of the figures where actually I think I could kind of access the meaning of it, even being an experimentalist. In panel C of figure 1.7, you basically are showing a spinning ball, which has two mirrors, one on the left and one at the bottom. And basically what you say, describing that figure, saying a rotating ball can exhibit clockwise or counterclockwise rotation, and the ball has handedness, so it's a handed object. But at the same time you say, because there is a mirror image of it that can be superimposed to itself, it is not chiral. So that means we have an object which is handed, but not chiral. And then I go to the few lines above the figure, where you basically write, it is important to know that though all handed objects can be chiral, not all chiral objects can be handed. And I found this a bit contradicting, right? Because in the figure you're saying I have a handed object which is not chiral, but in the thesis you're saying all handed objects are chiral. So is it me not understanding, or maybe was there something else about this?
Very learned opponent, thank you for pointing that out. It's an interesting observation. When I think about it, okay, now I'm thinking myself, yeah, as I'm speculating. I think the handedness and the chirality are quite actually independent. I can have a handedness and it can be chiral. But not all chiral objects have handedness. But I can also say the same thing. Not everything that has handedness are chiral.
Okay. So this goes a little bit in contradiction with what is written in your thesis. Maybe because I was literally learning from what you were writing down, and then I noticed this incongruence. So that's why I wanted to clarify. That's it. But I have to say, I'm not an expert on the subject, so I'm simply trying to understand together with you.
But I'll also read more about it. But when I read it right now, that's the kind of understanding that I got. Yeah.
Okay. Understand. Then I would like, if there is still time, to maybe ask a question about proposition number 3.
Chiral crystal can host nearly unidirectional spin configuration in momentum space, exhibiting a robust persistent spin texture that enables coherent spin transport through the material.
Thank you. I wonder if you could explain us in simple words what do you mean with, or what coherent spin transport through the material means?
Very learned opponent, thank you for the question. Coherent spin transport, in this context, I meant to say that we have a spin polarization in some direction, and when you transport the spin in a material, it doesn't change the spin orientation. It maintains its orientation. That is to say that if we somehow assign some kind of information to this spin, it doesn't lose as it pass through the material. That's what I mean by coherent spin transport. And for this particular proposition, we found that if you have a spin texture in momentum space where the spins are oriented mostly in the one direction instead of having all three components, this is almost like a perfect case where you can transport the spin coherently.
Okay, great, thank you. And so then, if you compare these persistent spin textures materials to typical spin Hall effect materials like platinum, what is the advantage of, for example, tellurium compared to platinum, based on what you just said?
Thank you for the question. As far as my understanding goes, when it comes to platinum, It's a very good material for generating a spin current because of its large spin orbit coupling, right? But it's not so good at transporting. You can generate the spin signal using the platinum, but it's not so good in transporting the spin signal through platinum channel.
Why is not so good?
Because of the large spin orbit coupling. And the spin can dephase because for different moment state, it has a different effective B field, right? As a result, spin can dephase. But if you have a persistent spin texture, like in tellurium, which is almost persistent, you can not only generate spin within the tellurium, but you can transport without dephasing. So that's a kind of difference.
Thank you.
Thank you, Dr. Leconte. The opposition will be continued by Professor Costa from the Fluminense Federal University.
Esteemed candidate, thank you very much for the invitation. It was really I enjoyed a lot reading your work. And one of the main figures behind almost all your articles in this work is symmetry. Symmetry is behind a lot of what have been doing. And this is very interesting because symmetry always prevails. If you are making analysis and your system does not agree with symmetry, you should be careful. But I have one question before going to the details of the symmetry. You talk a lot about the Rashad-Edelstein effect, spin Hall effect. Both of these two effects, they convert charge to spin current. Which one of these effects is preferable for a device application? How can you compare these two different approaches?
Highly learned opponent, thank you for reading my thesis and thank you for coming to my defense all the way from Brazil. And thank you for the question as well. Okay, you asked about the difference between the spin Hall effect and Rashad-Edelstein effect. And how can we compare or differentiate it in a given material? Well, spin Hall effect, the mechanism there is that it actually generates the spin current, the current itself. But the Rashad-Edelstein effect, there's no current. What you get at the end is a net spin density that is induced electrically, right? But at the end of the day, what you get is spin accumulation, because even in the Hall effect, you have a spin current, but the net result is you get spin accumulation. So in a given material, when, for instance, if an experimentalist measure the net magnetization, it would be, if there is no way to distinguish between the spin accumulation coming from Hall effect and the Edelstein effect, actually it could be a combination of both. Both will contribute. And unless the experimental setup is sensitive to this, to the ones that are coming from the Hall effect or Edelstein effect. But I believe it's experimentally quite difficult to distinguish between these two phenomena. Okay, another question would be, since your symmetry is behind a lot of what we have been doing, you identify tellurium as an extremely good candidate for this conversion via Rashad-Edelstein effect. Is there any recipe how to, because tellurium is one candidate, but I imagine that there are much more candidates out there. How can we try to find these new candidates? What's the guidance that the symmetry analysis gave to you that you can kind of apply, go through one of these materials database and search for new candidates that are more suitable than tellurium? Hi, Leonard opponent. Thank you for the question. Yes, symmetry is very important when it comes to guiding us through the material search about in what kind of crystal system we can have this Edelstein effect or not. But the symmetry alone is not sufficient to tell us how efficient this charge to spin conversion is or how big the spin current is in a given material. So for the high throughput, if you think about high throughput calculation, yes, symmetry can tell us, yes, it's allowed in this system and in this material, but it will not tell us how big it is. Yeah? For this one, we have to actually do the calculation for different materials and actually look at the result, right? In case of tellurium, after doing lots of analysis, the main reason why tellurium is a very good candidate for efficient charge to spin conversion thing is that it's their spin orientation in momentum space. That their spins are almost unidirectional compared to Rashba-like spin, which is where the spins are always perpendicular to momentum. But in tellurium, spins are like parallel to the momentum, and they're almost unidirectional. That's what we call as a persistent spin texture. And that kind of feature is desirable for spin transport.
So in this context, you would say that the collinear Rashba-Edelstein effect is superior to the conventional one for applications?
Thank you for the question. When it comes to which one is more preferable, I wouldn't comment on that, because as long as what we need at the end is a more efficient conversion from charge to spin and back and forth, right? There could be a very Rashba material that are very highly efficient. So on that note, I would not say that collinear is more efficient. But since my research is focused on the chiral crystal, they all tend to give a collinear Rashba-Edelstein effect. And compared to other Rashba material, I found it that tellurium actually has a very efficient charge to spin conversion. And one more thing about your previous question, actually you could do, when I think about it, I think you can also do a symmetry analysis to predict the spin texture for a given momentum. So maybe that is, I speculate, yeah? I think that's a very good way. You can just look at the different point group of a crystal, and if you know the point group, actually you also know the spin texture around that point. And if somehow you see that, okay, there's a persistent spin texture around that point group, then that's actually one recipe that there could be a efficient charge to spin conversion in that material. So yes, I guess symmetry can guide us even for the efficiency.
Okay, and I have one question about equation 1.11. It's a little bit, this question is a little bit over what might be necessary for the discussion, but you show that you have the spin density as expansion here, and then you calculated all the linear terms, the susceptibilities, and then you show that the symmetry implicates in these susceptibilities quite strongly. Depending on the symmetry, you have allowed terms, and other are forbidden. For some cases, they are forbidden at all. And now the experimentalists, they are working a lot in this non-linear regime. Do you think this symmetry analysis apply also to the second part, the second term, that would be the non-linear? The same kind of symmetry would be applicable to that tensor? Do you have any feeling about this?
Thank you for the question. You refer to equation 1.11. So the symmetry that applies to the linear response will not, in general, will not apply to the higher order terms because of the vector that we have are different. In the first order term, you have an electric field, but in the second, okay, there's I think it follows a different symmetry pattern. Even though I should acknowledge first that I have never, during my PhD, I didn't work on higher order response, right? But symmetry will be different.
Okay.
Yeah, because the expression is different.
Okay. Professor Costa, are you satisfied?
I'm satisfied.
Thank you. Then the opposition will be continued by Professor Janssen from the University of Groningen.
Thank you. Esteemed candidate, so I also read your nice thesis with great pleasure. I would like to start at the complete end. You have a nice summary, and completely at the end of the summary, you summarize your thesis essentially, with the insights gained from this work highlights design principles for realizing spintronic devices that combine efficient charge-to-spin conversions and long spin coherence lengths. Taken together, these findings pave the way for for experimental studies of CSC and spin transport in bulk chiral crystals, and open new avenues for both materials discovery and device engineering in the next generation of spintronics. Now, this sounds great.
Excuse me, which
It's completely at the end
a summary?
of the summary, the last couple of sentences. Yeah, so it sounds great. I mean, you have opened the avenues for new experimental applications, but according to you, what are now the most important new challenges for theory that should be taken up in the near future? So what are the, say, you get money for 4 more years, what would you do with this as a, say, next research project?
Highly learned opponent, thank you for the question, and thank you for reading my thesis. If I'm given 4 more years, I would continue to do research in this charge-to-spin conversion, but with a different approach. For instance, for my PhD research, I studied mostly spin transport and spin phenomena. But over the last couple of years, the community has been really focusing on orbital effects, like orbital Edelstein effect, and orbital Hall effect, and chiral crystals. It seems like they are, like, again, a very natural and perfect platform to study these orbital effects. So if I have time and resources, that's something that I'm really interested in. That's the first thing. Second thing is I am also interested in the higher order effects, like the second order Edelstein effect and second order Hall effects, because experimentalists these days, when I read the papers, they measure a lot of these things that are related to higher order effects. And it will be very nice if I can somehow study more on these higher order effects.
Okay, thank you very much. So that sounds very exciting. I would now like to proceed to stelling number 1. Can one of you read the proposition number 1?
The absence of the inversion and mirror symmetries in chiral crystals makes them an ideal platform for investigating the intricate relationship among symmetry, electronic transport, and spin-orbit phenomena. The reduced symmetry of such systems enables several unconventional optical and spin-related effects.
Okay, thank you very much. So can you give me an example of an unconventional optical effect that you have in mind?
Highly learned opponent, thank you for your question again. Because of the reduced symmetry, there's no inversion symmetry, even though I did not work in again optical aspects. So what here is I read literatures about different things that the crystal without inversion symmetry could lead to. And there are certain optical effects that are very specific to the system without inversion symmetry. For instance, there's a non-linear optical effect such as natural circular dichroism, which is available only in the system without inversion symmetry. So the idea here is that when you shine a light in these chiral crystals, the polarization of light will rotate, and the rotation of this polarization vector it depends on the direction of the light. So that's the one effect that's unconventional. And for me, even this Rush-Rayleigh effect, in a way, is it's very much related to the optical things, at least from the perspective of symmetry, because the Rush-Rayleigh effect that I studied in the chiral crystals, they all lead to collinear chiral crystal, but it's not only chiral crystal that can host collinear. There's a group of, it's called gyrotropic groups, gyrotropic crystals, which can host this collinear Rush-Wilson effect. And in these crystals, then there is a gyration of electromagnetic waves as it passes through the materials.
Okay, thank you very much.
The doctoral board will withdraw some time to consider its decision. Esteemed PhD candidates, the doctoral board of this university, represented by us, after reading your PhD thesis and the accompanying propositions, and after hearing you defend it, has decided to award you the PhD degree at the University of Groningen, which you desire. And because of your very important contribution to the field, as exemplified by your publications, and because of the outstanding defense with the highest distinction from your faculty of studies, namely cum laude. Your primary supervisor, Professor Slavinska, is authorized to award you with this honor in the customary fashion.
I'm happy to accept the task assigned to me by Director Magnificus. However, before performing this task, I would like to address a few personal words to you. Dear Karma, today is a very happy day. For you, because you are officially completing your PhD, and for all of us, because we get to celebrate the impressive work you have done over the past 4 years, exactly 4 years right on schedule. When you arrived in Groningen, you had no background in spintronics and no background in density functional theory. In most situations, that combination would be a recipe for trouble. But instead, within just a few weeks, you learned DFT well enough to run good quality calculations, and soon after, you were already contributing to substantial discussions on spintronics. What stood out from the start was your attitude. You never waited to be pushed. You were always the one moving things forward. You asked the right questions, tested ideas on your own initiative, and often came with results already in hand. That combination of curiosity, independence, and determination shaped the entire trajectory of your PhD. Scientifically, your contributions have been substantial. You worked on challenging topics, learned quickly, and connected concepts with maturity and depth. You progressed at a pace that was the opposite of the snail that you chose for your thesis cover. With 10 very good papers completed during your PhD, you have built a research record to be really proud of. It reflects both your talent and dedication. And beyond the scientific achievements, you are a pleasure to work with. Calm, supportive, patient, and always willing to help others. You contributed greatly to the positive atmosphere in our group. People trusted you, not only because you were capable, but because you were kind, respectful, and reliable. Working with you has been easy, enjoyable, and inspiring. As you move on, I have no doubt that you will continue to grow and excel. You have everything you need: intuition, strong discipline, and the humility to keep learning. Karma, congratulations on completing your PhD cum laude. You have done an outstanding job, and I wish you every success and happiness in the years ahead. By virtue of the powers vested in us by Dutch law, in accordance with the decision of the College of Deans of this university, I, Jagoda Sławinska, confer on you, Karma Tenzin, the title of doctor and all the rights associated by Dutch law or custom with a PhD degree at the University of Groningen. Do you, as a doctor, promise to act in accordance with the Netherlands Code of Conduct for Scientific Practice?
Yes, I promise.
Now that I have performed the task assigned to me, let me be the first to congratulate you on your PhD degree and to address you as a doctor.
Thank you.
As proof of this PhD degree, awarded with distinction, I will present you with a certificate signed by the Rector Magnificus, Secretary and Supervisors, and sealed with the Great Seal of the University. But before doing so, a very learned scholar, Dr. Tenzin, it is my pleasant duty to congratulate you also on behalf of the Doctorate Board of this university. Somewhere around here it says laude, you see? Yeah, that is the extremely impressive bit. Then we have something signed by with the wishes from people on the committee. There you go. I now declare this ceremony closed.